Welcome to the walkthrough for assignment 2B, which focuses on a new variant of the image crawler stream app. The purpose of this assignment is to deepen your experience using Java functional programming features and their integration with Java's parallel streams. In particular, in this assignment, you'll develop an app that uses several Java parallel stream strategies to obtain, transform, and store images. The code you write for this assignment has a GUI and runs as an Android app. Please feel free to use this app to help debug your solution. The following resources may be helpful in completing this assignment. Detailed overviews of the Java Parallel Streams framework are available in my YouTube playlist here. Naturally, we'll cover this material in class, which will also be available in my YouTube CS253 playlist here. Good overviews of Java sequential and parallel streams appear here and here. I highly recommend you get the book Modern Java in Action to learn more about Java streams programming. Before you can complete the initial submission of Assignment 2B, you'll need to do the following. Complete your implementation of Assignment 2A, taking into account my review comments. In particular, it's important that your unsynchronized array implementation works properly, since this class is used as the basis for the app in this assignment. Please come to office hours or post questions on Piazza if you have any remaining questions about your Assignment 2A solution. The Image Crawler app is packaged as a project using the latest version of Android Studio. The app is written in both Kotlin and Java and demonstrates many Android capabilities. For the purposes of Assignment 2B, however, you only need to be aware of the following directories: the image crawler utils and image crawler crawlers directories, which contain the skeletons you need to fill in, as described below, the image crawler source test, which is a set of unit tests that exercise the features you're implementing and are used to evaluate whether you've correctly satisfied this assignment's requirements, and the app source Android test Java assignment test, which contains an Android Studio instrumentation test that runs your app automatically. As always, to compile the code, you'll need to use the provided Android Studio project. You can run this project by clicking the green Run App button in the Android Studio IDE, which should automatically select an emulator to run, assuming you've already created one. The application's minimum API is 29, so you'll need to select an emulator that uses an API that's at least 29 or ideally 30. If you don't already have one created, you can create it by clicking the AVD Manager button in the Android Studio IDE. In this part of the assignment, you'll complete the implementation of an image crawler class in the Parallel Streams Crawler 1 Java file in the image crawler source main Java edu Vanderbilt image crawler crawlers folder. This class applies a couple of minuscule tweaks to the sequential streams crawler that you did in assignment 2A. In this case, Java Parallel Streams will be used to perform an image crawl starting at a root URI in order to obtain, transform, and store the images. Depending on the parameters that you use to run the tests, the images from the HTML pages reachable from the root URI are either downloaded from a remote web server or read from the local file system, and the results are stored in local files. Also in this part of the assignment, you'll complete the implementation of an image crawler class in the Parallel Streams Crawler 2.java file, which is also in the image crawler crawlers folder. This class uses a more advanced Java parallel stream implementation to perform an image crawl starting from a root URI to obtain, transform, and store images. The bulk of the code for the app is provided in the skeletons. You should convert your sequential stream crawler class from assignment 2A to the parallel streams crawler.java class in assignment 2B by making minuscule changes to use Java streams. You'll also need to complete the to-do tasks in the Parallel Streams Crawler 2.java file, which is a variant of the Parallel Streams Crawler 1.java file that uses Java streams in a more sophisticated manner. You also have to complete the collector implementation in the utils array collector.java file. Graduate students should use the utils synchronized array class implementation from their last assignment in their array collector.java implementation. Conversely, undergrad students can ignore the synchronized array class and simply use the unsynchronized array class. Your solution should use no loops or no unnecessary conditional statements in this assignment, and instead use Java's parallel streams operations and functional programming features. The skeletal code for this assignment can be obtained here in my GitHub repository. Now that you've set up your GitLab account, you can pull the skeleton code into your repository, read it carefully, and complete the to-do markers. As always, there's a set of JUnit unit tests in the image crawler source test Java edu Vanderbilt image crawler folder and these are provided to increase our confidence and your confidence that your implementation is working as expected. You can always tell very quickly whether or not you're doing good and whether you're going to get a good grade by running the unit tests. You'll need to learn how to use the Android Studio GUI to run this test, as I'll show you later in this video. As always, testing only demonstrates the presence of bugs, not their absence, so don't rely solely on the unit test to detect problems in your code. Look carefully and think about what you're doing. Obviously, respond to my comments on your code, watch the video that I put out with frequently made mistakes, and also don't be surprised if we add more unit tests in upcoming assignments in order to further test your assignment and your previous implementation strategies more thoroughly. Assignment 2B is designed to deepen your experience developing apps using Java's functional programming features and Java's parallel streams without requiring you to program the underlying common fork join thread pool directly. The skeletons and unit tests are extensive, though you don't need to understand them all to complete your solution. Please start early and ask questions in class, office hours, and on the Piazza discussion forum. Now that we've walked through the specification for Assignment 2B, let's go ahead and take a look at the skeletons. We'll start by taking a look at Parallel Streams Crawler 1. This is an image crawler implementation that uses Java parallel streams to perform an image crawl starting from a root URI. In this particular case, the implementation is very straightforward. All you need to do is take a look at your sequential streams crawler.java file after addressing all my comments and after watching the frequently made mistakes video for assignment 2A. And then after you've made those enhancements, go ahead and make the minuscule changes required to use parallel streams instead of sequential streams. So the skeleton looks pretty much identical to the one from assignment 2A. The main difference is I think I improved the comments a tiny bit. And if you take a look down here, it's a little bit more clear about how to do some of the steps. But basically, copy in your code from assignment 2A after you've addressed my comments and so on, and then go ahead and just change stream to parallel stream in both places where you use stream. So very simple. This is really just there to demonstrate how ridiculously easy it is to take a sequential stream that's working properly and then make it run in parallel. And when you run the tests and when you run the instrumentation tests and run the app, you'll see how much faster it runs compared to the sequential version. So that's really just a very simple example of assignment 2B. Let's go take a look at something more interesting now. This is Parallel Streams Crawler 2. And this also does the same thing from a logic point of view, but it's going to be a variant of Parallel Streams Crawler 1 that's going to use parallel streams in a more sophisticated manner. So it'll give you a chance to do more cool stuff with streams. So let's go down here. Once again, the perform crawl method is going to be the same as before. Here is crawl page. As you'll see here, this is going to have a Java parallel stream that returns the number of processed images by the following steps. So this is going to be a little different from what you did before. It's not just a mindless changing of streams. It's a parallel stream as you did for Parallel Streams Crawler 1. And instead of what you're going to do is you're going to create a stream of two function lambdas. One function lambda will process images on a page, and the other function lambda will process hyperlinks on each page. Then you're going to go ahead and run the stream elements, these lambdas, in parallel, and you'll invoke each function lambda mapping the result to an integer, which of course is a count of the number of images that are downloaded and processed properly. And then you return the total number of processed images at this point. As you can see, we have a couple of helper methods here to make this easier to deal with. This is something called stream of tasks, and it's a factory method that constructs a stream containing two function lambdas. One again for processing images on a page and the other for processing links on a page. And you can see that this will return a stream of two function lambdas that do what I just talked about. So in this case, you'll have to change this factory method to return a stream that implements these function lambdas. Down here, we have a factory method that creates or constructs a function lambda to process images on the input page. And so you can see here the factory method is called make images on page function, and it's going to return a function lambda that receives a page and gets and processes all images on the page and returns a count of the processed images. And then down here, we're going to have another factory method called make hyperlinks on page function. And this is going to construct a function lambda that will crawl the hyperlinks on the input page. And you can see here the comment says it's going to return a function lambda that receives the page and recursively crawls the hyperlinks on this page and counts the number of processed images on each hyperlink or from each hyperlink. And you'll have to pass an adjusted depth value to reflect the depth of the children hyperlinks on this page. That's very similar to what you did in the previous assignments. Down here, we have the process images method. And you can say this takes an array of URLs. And what it's going to do is it's going to download, process, and store each image in the URLs array that's passed as a parameter. And it'll return a count of the number of images that were processed. And there's a kind of a detailed comment here that explains what you need to do. You need to use a Java parallel stream that will convert the URLs array into a parallel stream, map each URL to a downloaded raw image, make sure you ignore any null images as always, convert each downloaded raw image to a stream of transformed images, and then return the number of successfully transformed images. The key is successfully. And then here we have a method called crawl hyperlinks on page, which takes a page and a depth. And this is going to recursively crawl the hyperlinks that are on the page. And what this is going to do is it's going to use a Java stream that will invoke perform crawl to crawl through the hyperlinks on this page and return the total number of processed images. And this should really say a Java parallel stream, of course. And the Java parallel stream you're going to use here will return the number of processed images by the following steps. Get all the hyperlinks on this page as an array of strings, convert the array to parallel streams, call the helper method to crawl each hyperlink and map the result to an integer, and then return the total number of processed images. And then here is this helper method called transform image. And you can see here it's basically going to download, process, and store an image by applying all the transforms to it. This should look very familiar at this point. This is going to take an image, and what you're going to do is use a Java parallel stream to perform the following steps. Convert the transforms list into a parallel stream, create a new cache item for each image if you can, filtering out any images that have already been locally cached, apply the transform to the original image to produce a transformed image, and then return a stream of all non-null transformed images. So make sure that you get rid of things that are null. And if the calls are returning nulls, you have to get rid of them somehow, typically by using filter, of course. So that's essentially what you'll be needing to do for this implementation. It's more complicated than the one you did before, but it'll also give you a chance to try out some other cool features of parallel streams, as well as Java functional programming for that matter. Let's go ahead and take a look at the last class you'll have to implement after we've talked about collectors in recent classes. Now it's time to actually put that theory into practice. So you're going to have to implement something called an array collector, and that is a mutable result container that will accumulate input elements in such a way that you'll end up with a collector of all the elements in a stream that are organized in the way you want it to be. And this can either be performed sequentially or in parallel. The grad students will implement a concurrent or parallel collector. The undergrads will implement a non-concurrent or sequential collector. Please be aware, of course, that non-concurrent collectors can be used with parallel streams. The streams framework manages all the synchronization properly behind the scenes, so you don't have to worry about it. So let's take a look at the method you'll have to implement here. You'll have to implement a method called toArray, which will create a new array collector. This is basically kind of akin to the toList factory method that's on the collectors utility class, or toSet or toMap. So this is toArray. So it's going to make a new array collector. Hopefully that's pretty clear what you have to do there. Down here in the supplier factory method, this is going to return the appropriate factory method, or the constructor that will make the appropriate type of mutable result container. And in this particular case, the graduate students need to use a synchronized array because they're implementing a concurrent collector, whereas the undergrad students have to use an unsynchronized array because they're implementing a non-concurrent collector. So there's two different branches there that you have to be aware of. Down here we have the accumulator factory method. This is going to return the accumulator that's going to fold a value into the mutable result container. And so you'll sort of have to think about how you can do that. It shouldn't be too hard if you go back and watch the videos and see how we did it with the other examples that we talked about in the lessons in class. You have something similar for your array class that's very similar to the list class that we used in the examples. Then you have a combiner, and that's what takes two partial results and merges them. As it turns out, the undergrads have to actually implement this to do the true combining. And that's because the undergrads need to be able to merge stuff together because they're using non-concurrent collectors, and that requires a combiner. Graduate students don't need to change anything here because they're doing concurrent collectors, and so the combiner is never called for a concurrent collector. So you can just leave it like this. Then we have another method here called the finisher, and that's going to perform the appropriate transformation to return the intermediate result that we want here. And this is very straightforward. You just have to replace null with the proper code. And then down here, we have the characteristics factor method. And this is going to set the appropriate characteristics. So in this particular case, the undergraduates have to say unordered and identity finish, and then the graduates also have to add concurrent because they're creating a concurrent collector. So again, if you go back and you watch the video about concurrent and non-concurrent collectors, especially the non-concurrent ones, because it's the same thing for this, you'll see how we show some examples of how to create the characteristics set that's required for this. Okay, so that's basically what you're going to have to implement in order to make all this work. If you have any questions, please don't hesitate to ask. Make sure you come to office hours. Make sure you go to Piazza and post questions, or come see the TAs. And hopefully that'll give you a good head start on how to do the assignment. Now that we've walked through the specification and the skeletons, it's time to show how to run the unit tests. As usual, if you go into image crawler, source, test, and then you go ahead and click on run all tests, which you get by doing a right click or whatever is appropriate on your IDE. You can go ahead and start the various test building. There are a lot of tests to be found here in this example. And of course, each time we put out a new assignment, we typically add new tests, as well as sometimes update previous tests so that they're more comprehensive. You can see here we have 134 tests, not all of which run, depending on whether you're running things as a graduate student or an undergraduate and so on. But what this is doing, is, of course, is it's going ahead and running the tests for parallel stream crawler 1, parallel stream crawler 2, sequential stream crawler, the various array collector tests for grads, the array collector tests for undergraduates. We've got a bunch of synchronized array tests for grads. Of course, there are lots of synchronized and unsynchronized tests for grads and undergrads, and so on and so on and so on. So as you can see, lots of stuff. In order to get full credit, all the tests have to be green, and so you may, of course, run across some questions. Please don't hesitate to come to office hours or post on Piazza to find out what you need to do to make things work. Also be aware, as I mentioned before, we will often add new tests to older assignments because we come up with better ways to collect and capture the problems that people have run across. So just because something worked in assignment 1 or assignment 2A doesn't mean that for assignment 2B or beyond, that those pieces of code that you write will still always be guaranteed to work, or at least guaranteed to pass the test. They probably never really worked. It's just that our tests weren't comprehensive enough to catch them before. So we're fixing that as we go along, and that's why you always have to be aware that tests simply show the existence of bugs that are covered by the tests, but never show or never prove that there aren't any bugs or any defects, because the test simply may not be comprehensive and thorough enough in order to capture them. So that's basically the walkthrough of assignment 2B. If you have any questions, please don't hesitate to ask.